Okay, so now we start section on mean value theorem. Okay, so the topic is the mean value theorem. So most of the time we will denote this by MVT. Okay. So we will use mean value theorem very often, so we need a shortcut for this. So mean value theorem depends on a very simple theorem. Okay, so we start with Rolle's theorem. So Rolle's theorem says that if f is differentiable on an interval and continuous on AB. Okay, so here normally when we are talking about our functions are continuous and differentiable on the closed and bounded interval. Differentiability at an endpoint is given by one-sided limit. Okay. But you see sometimes the function may not be differentiable at an endpoint. Okay, so even in that case, this theorem holds. The crucial thing here is that the function is continuous at everywhere. So if the function is differentiable here and also continuous here, but at the endpoint it jumps, that's not within the domain of this theorem. Okay, so this theorem wants a continuous function, and in between you can take the derivatives. Okay, so then there is a point C in the inside at an interior point such that f prime C is equal to 0. Okay. So the proof of this is easy, but when you keep writing it down, you have to cover all cases. Okay. So how do we prove this? How do we make sure that this is true? Okay, so instead of this whole thing, we write proof. Okay, so that's why we shorten this. So what do we expect to this? The only thing, if you are trying to make sure that something is correct, you have to use the things that you have done so far. Okay, so you cannot use something that you will prove later on to prove this, and then when it comes to there, you will probably use this. Okay, so there is a cat chasing her tail. So in our case, the only big theorem about f prime being 0 is minima and maxima. And what do we know about minima and maxima so far in general knowledge? That a continuous function on a closed and bounded interval always has a minimum and maximum. Okay? So in our case, we have a continuous function on a closed and bounded set. Okay? So it has a minima and maxima here. Then at one of those points, f prime will be 0. That's the theorem that we proved last hour, Fermat's theorem. Okay? So here the only thing to make sure is that C is in the interior, not at the end point. Okay, so about that we can do easily, because if the derivative is 0 at one point, both of these points cannot be both minimum and maximum, except when the function is constant. If the function is constant, the derivative is 0 everywhere, so this is satisfied. If the function is not constant, then both endpoints cannot be at the same time minimum and maximum. Okay, so one of them must be larger than the other. Okay, so here, yes, the proof, when I was talking about the proof, I realized that I need one more condition here. So you see that the theorem, in the way I stated, is wrong. Consider the function y equals x. Okay, the derivative is never 0. So what do we want? We want the endpoints to be the same. So let us add here, and f of a equals f of b. Okay, so that's the thing that makes Rolle's theorem roll. Okay, so now, okay, so first case, if f is constant, then f prime equals 0 at every point. Okay, so this is done. I have choose any point inside, it is done. Okay, 2. Now, f is not constant. Okay, then there is a point C inside A, B, where f takes a minimum or maximum. Okay, so the picture, let us draw here the cases that we are thinking about. So it can be like this. So here, this is minimum. The function takes its maximum at the endpoints. So there, the derivative is not 0. It can be like this. The function takes its maximum here, minimum at the endpoints. Since the minimum is at the endpoints, it's not guaranteed that the derivative will be 0 there, but here it is 0. So we have this case, or a typical case, it does something like this. So endpoints are the same, but you see there are lots of points where the derivative is 0, local minimums, local maximums. Okay, so I summarized all of them here by saying or. Okay, at that point, at one of those points f prime is 0. Okay, so in the book you will see a little bit more detailed proof, because the book has to cover this case also. Okay, because this is when you are stating a theorem like this, this is what you have in your mind. Okay, if it is at the endpoints, if the function rises, then since at the other endpoint it will have to come down, somewhere it will turn. Whenever it turns, the derivative will be 0. Okay, so that's what you have in your mind. Okay, then you check if in all extreme cases the function does actually turn. Okay, so in this case it turns, in this case it turns, and in this case it turns several times. Okay, so when it comes to the proof has to be rigorous so that you will make sure that you covered all cases, because sometimes you write reasonable cases here, but one extreme case you never think of. Okay, that shows up in the proof. So that's why the proof has to be detailed. Okay, so that is the Rolle's case, Rolle's theorem. Okay, so let us look at examples where we use this thing. Okay, so here, okay, let's do example 2 in the book. Okay, so it says, show that the equation x cubed plus x minus 1 has exactly one real root. Okay, so show that x cubed plus x minus 1 equals 0 has exactly one root. Okay, so any ideas? So let me see what the book is doing for this. Okay, so first we have to show that it has a root. Okay, so this is a cubic equation. So does every cubic equation have a root? Can you think of a cubic equation which has no real roots? Somebody said no. Okay, so why is it no?
Because we give a value to this polynomial and it will evaluate negative, and then we will set other value and it will give us positively.
But maybe can't we do that for every polynomial? Then you are saying every polynomial has a real root.
No, but we can do every polynomial because it's a parabola. Then it's above the x-axis. Then it's always positive.
So you must think of something specific to a cubic polynomial. So why can you always make a cubic polynomial both positive and negative? Well, minus infinity what?
And infinity will make a difference.
So you mean the limits, okay? So build sentences. In math classes, we are not charging you, we are not taxing you for every word you use. Words are free, okay? So what you mean is dominating term is x to an odd power. So when you give a very, very large, in absolute value, a negative number, it will be negative, okay? So that's what, then you have to say all of these. Or to summarize this, when x goes to minus infinity, the value of this is minus infinite. When x goes to plus infinite, it is plus infinite. Okay, so somewhere in between, it has to cross the x-axis. Okay, so the general theory says that it crosses the x-axis at least once, but it may cross x-axis 2 more times because it's a cubic equation. Okay, so this thing is. So let me call this f of x. Limit f of x as x goes to minus infinity is minus infinite. Limit x goes to infinite f of x is plus infinite. So somewhere in between, it must cross x-axis. Okay, so this is intermediate value theorem. You have to be able to quote these theorems to convince other educated people. Okay, so by intermediate value theorem, it may cross x-axis. So it may be like this. So the graph of f is either something like this or like this. Okay, so here only one root, and here we have 3 roots. Okay, so this is also in accord with the general theory saying that if a complex root exists, then its conjugate is also a root. This is true only for polynomials with real coefficients. Okay, don't make later on when you grow up, don't make the semi-educated mistake of quoting the same result for polynomials with complex coefficients. Okay, polynomials with complex coefficients obviously can have a complex root, and its conjugate may have nothing to do with the polynomial. Here, the reason why the conjugate occurs is that if you have only one complex root, then you have to do a lot of algebra to show that you can't get rid of the complex numbers in the coefficients. But here the coefficients are real numbers. Okay, so if one root is complex, the other one must be complex conjugate so that imaginary numbers will be killed. Okay, so which one is it? We will check. Okay, so any questions? So you see, if this is the case, the derivative will be 0 here and here. Okay? So let's check the derivative. F prime x is equal to 3x squared plus 1. Okay? So what do you say now? If this is the case, so this function cannot be 0. So this situation cannot be whole, because here, you see here, and here f prime is equal to 0. Okay? This is never 0. So f has only one root. Okay, so where did I use Rolle's theorem? This is supposed to be an example of Rolle's theorem. I used the Rolle's theorem in the picture. I didn't write it down. Okay, so here I said if it has two roots, the function rises here, it must turn down and come here to meet the other root. Okay, that's what the Rolle's theorem is saying in more polite words. Okay, the value of the function is 0 here, the value of the function is 0 here, so f of a equals f of b. So somewhere in between the derivative is 0. If you want to write this thing in a technical manner, that's what you will write. Okay, but here I summarize this in the picture. So the derivative must be, according to Rolle's theorem, the derivative must be 0 somewhere in between. But when I write the algebraic expression, it's never 0 on the real line. So f cannot have two roots. And because of the odd order here, it is guaranteed that this has one root. Okay, so Rolle's theorem is useful in such situations, but the main purpose of Rolle's theorem is to prove the mean value theorem, which is the main thing. It is surprising how many times we will meet mean value theorem. Okay, so state and prove the mean value theorem. So let me follow the recipe. Let us first look at this thing geometrically. Okay, so we have a function. Now I want to exaggerate this so that the picture will be nice. Okay, so this is the function y equals f of x. Okay, and I consider the second line from here to here. Okay, so I consider this second line. Okay, so second line. Now I consider tangent lines. Okay, so in mathematics you play games hoping that something interesting will come up. If something interesting comes up, you tell it to others. If nothing such a thing comes up, you just have fun yourself and pass to other things. Okay, so at this point you see that this is the, okay, so this is the tangent line. At this point, this is the tangent line. Here, the tangent line. Here, the tangent line. Now, in this picture, I observe the following thing, only in this picture. Okay, so from this picture, I'll make a conjecture that in all pictures, a similar thing holds, and then I'll try to prove if that's really the case. Okay, so that's why you have proofs. You study a spatial nice example, you see a pattern here. You hope that that pattern will be repeated at every similar situation, but to check that, you have to give a proof. In the proof, we'll use Rolle's theorem. Now, the observation I have here is this thing. Okay, so let me use a blue pen. Okay, so the blue pen is directed in this way. Now, the tangent line starts like this, okay, and here ends like this. So somewhere in between, they must be parallel, okay? So I start like this. This is tangent, tangent. Here, they are parallel, and then it is like this, okay? So I don't know exactly where they will be parallel because this thing can be a little bit like this, okay? So there are calculations like this. For example, Euclid says that if you have two lines and if you have this thing in between, okay? So if this angle plus this angle is not equal to the sum of two right angles, then these lines never meet. Okay? So this means that if the sum of this angle, if the sum of these two angles is less than two right angles, they will meet. Okay, now just calculate this. Suppose this is less than, the sum of this is 2 pi minus 0.01. Calculate where they will meet. Okay, they will probably meet. If 0.01 is not enough, make it 0.001. Okay. Euclid says that they will meet 2,000 years ago, but when you calculate it, they will meet outside the known boundaries of the universe. Okay, so these things need some algebraic calculations. Here I cannot tell that they are parallel. I can only conclude that here they were like this, and here they are like this. So somewhere in between, they are going to have parallel slopes. They are going to have the same slope. Okay, so somewhere in between. Okay, so the claim is, so we observe that somewhere in between the slope, or rather the tangent line, okay, the tangent line is parallel to the second line. Second line is what? Blue. Okay, so I'll write it blue. Okay. Now the question is it always the case? What did I use here? I used that a tangent line exists everywhere. Okay, so that's the only thing I used. I can always draw the second line, so I'm trying to check if this is true for no matter what the picture is. This is a very nice picture. Okay, so nobody questions me with this, but if I say consider f of x, which has derivatives at every point, okay, is the tangent line of this somewhere going to be parallel to the second line joining the endpoints? Okay, so that's the claim of the mean value theorem. Okay, so let's write it over there. Okay, so the mean value theorem. Let f be continuous on A, B, differentiable on A, B. Okay, so this is again not a restriction. If f is differentiable everywhere, that's okay. So this is saying that I will not especially ask if the function is continuous at the point A or not. If the function is continuous, differentiable there, that's okay. I don't care. Okay, then the slope of, what is the slope of the second line here? Let's go back here. Of the second line is. Okay, so let's put numbers here. This is A, this is B. This point is A, f of A. This point is B, f of B. Okay, so what is the slope of the second line? Okay, so this distance divided by this distance, right? So this is f of B minus f of A divided by B minus A. Okay, so let f be continuous there, differentiable there, then there exists a point C on the interior such that the slope of the tangent line B minus A is equal to the derivative at that point. Okay, so this is what we observed on that very simple special curve, and we are checking if this is going to be the same for all other curves. Okay, so again, let's continue with the same curve. Okay, so we have something like this and this. Okay, so these are endpoints B, f of B. This is A. Okay, let me write A to the other side. A, f of A. Okay, so suppose this is y, this is x, and this is y equals f of x. Okay, so now one easy way to prove this is to use Rolle's theorem. Okay, for Rolle's theorem, I have to find a function which is the same at endpoints, relating this second line and this function. The easiest thing I find is their difference. Okay, so at a given point, so this is A and B, this is A, this is B. At any point x here, okay, consider this function. Okay, so here I write this difference. Okay, so that difference is 0 here. It is also 0 here. Okay, f of a, well, now I'll call it something else, say g of x. G of a equals 0, g of b is equal to 0. Is this a continuous function? Well, this is a straight line. I'll write the equation of this. I know the slope of this. I know one point where it passes. It's a linear equation. It is continuous. F is continuous, given. That's, I impose this. Okay, so the difference of two continuous functions is a continuous function. So if I call this g of x, okay, so if I call this g of x is continuous. It is differentiable in between. Here, it is differentiable here because f is differentiable. Straight line, the equation of straight line is differentiable. Okay, so I have a continuous function which is differentiable equal to the same number at the endpoint, so its derivative is 0 somewhere in between. Okay, so that's as far as I can think at this point. At this point, I say, okay, let me do my prayers and start writing this. And hopefully, after I take the derivative and make it equal to g prime at some point, I'll be able to simplify and get an idea about what to do. If I'm very lucky, after I simplify, I'll get this expression. Okay, so let us write that now. Okay, so again, we call that a proof. Consider g of x equals f of x minus. Okay, so equation of the straight line. What is the slope of that straight line? That number. Okay, f of b minus f of a over b minus a. And it passes through, say, one of those points, A. Okay. And at the point x equals a, the value of this function is f of a. F of a. Okay. So this is equation of the equation of the second line. Okay. I know the slope and I know a point where it passes. This is the equation. Note that I make these notes because I'll use this in Rolle's theorem. G is continuous, A, B, differentiable on A, B, okay, and G of A equals G of B. In fact, both equals 0. Okay, so let's check if it is really 0. I wrote this by looking at the picture. In the picture, it is 0. But let's check if the equation is correct. F of x, instead of x, if I put a, I have f of a here. This vanishes. I have f of a here. So f of a minus f of a. If I put x equals b, here I have b minus a. These cancels. F of a's cancel. I have f of b here, minus f of b, plus f of b, 0. So g of a equals g of b. So all conditions of the Rolle's theorem are satisfied. So this is how you use theorems, okay? So you have a function, you want its derivative to be 0, and Rolle's theorem says the derivative is 0. If you have a function, you say, by Rolle's theorem, the function is 0. That is wrong, okay? So that's one of the grave mistakes you make. Rolle's theorem does not say that the derivative of the function is 0. The Rolle's theorem says that if the function satisfies this, and this, then the derivative is 0. Fortunately, in Rolle's theorem, the conditions are very simple. Okay, so you check that those conditions are satisfied. Now you say by Rolle's theorem, g prime c equals 0 for some totally unknown c in the interval. Okay? Okay, so this is the point up to where our intuition guided us. Now let's do calculation. Keep our fingers crossed that when I take the derivative of g, I'll get something nice. Okay? So, okay, let me take derivative of, so let me say, but derivative of this is f prime x minus, okay, if I take the derivative of this, I'll have f of b minus f of a over b minus a, and this is constant, derivative is of that is 0. This is the derivative. Okay, so suddenly the problem resolved itself by itself. We didn't do anything. Okay, now put x equals c. Okay, we found this c here. We don't know where it is. Okay, so this is the price you pay for these things. At some point, the derivative will be 0, but we don't know where. We only know that there exists a point where the derivative will definitely be 0. So when you put this thing in, you have g prime c equals f prime c minus f of b minus f of a over b minus a. Okay? So we know that this is 0. We know from here, okay, so from here we know this is 0. Okay, so f prime c is equal to this. Okay, so f prime c is equal to slope of the second line as we hoped, as claimed. Okay, so this is the mean value theorem. So the nice thing about this is, you see, suppose in this example I fix a, so this is how we will exploit this. Suppose I fix a there, okay, so this a is fixed. So this theorem holds for every b. So instead of b I can write x. Obviously every time I put a different number for x, this c will change. Doesn't matter. This is saying that there is always a point between x and a, so that the derivative will be 0. Okay, so I turn this around. It will tell me that the value, so here we can make b move. Okay, so call it x. So we have f of x minus f of a over x minus a equals f prime c for some c between a and x. Okay, so this is traditionally how we write it, because now when I start changing x, I'm not claiming that x is going to be larger than b. B can be on this side, because you check that in the proof we didn't use anywhere that a is less than b. We just used that a and b are different, and c is between a and b. When I draw a picture, of course, I have to write one of them to the left, one of them to the right. But in the algebraic procedure, that property is never used. So x can be on this side of a and y, or on the other side of a. In either case, c is between x and a. Okay. So from here, I can write f of x equals f of a plus f prime c x minus a. Okay, so this will be one of the starting points in next semester, trying to understand the function. So around the point A, at the point A, the function takes this value, and around A, it behaves like this. But here, this c is always changing. Okay, so next semester we will say, suppose we go one more step, what happens? Okay, so that will be, I can approximate this function. So here I'm approximating this function with this number, and the error I'm making is this. But if I approximate this function with a linear function, when I fix this point here, then I'll be making an error here. That error will depend on second derivative. One of the way to prove it is again to use mean value theorem. Okay, so that we will do. Okay, so now as an example, we want to prove a trigonometric identity about things. So another example. So suppose f of x equals sine x on a, b. Okay, sine is a periodic function. So we look at f of b minus f of a over b minus a is equal to f prime c for some c in a, b. So this is mean value theorem. Now let's put these things in here. I have sine b minus sine a over b minus a equals cosine c for some c between these. Take absolute value of these. Okay, so the absolute value of this b minus a is equal to cosine c. Well, this is how you use mean value type theorems. Next semester we'll do, as I said, an extension of this up to the nth derivative. So then that will be Taylor's theorem. Then again it will end with an unknown point. You evaluate the nth derivative, n plus first derivative at an unknown point. Since you don't know anything about the value of cosine at that end point, at that unknown point, you use other properties of this function. In this case, cosine, no matter what value it takes, its absolute value will never be larger than 1. Okay, so we impose that here. This is less than 1. Okay, so cosine being eliminated, now we have a property here which says that, hence, okay, we don't like writing sine b minus sine a. Everybody wants to write sine a minus sine b. Inside the absolute value sign, it doesn't make a difference. This is always less than or equal to this thing here. So this is again a minus b. Okay, so this is a property we observe about sine, the values of sine. Of course, if a and b, the difference between a and b is very large, this is not interesting because sine a minus sine b is never larger than 2 in absolute value. So this thing is interesting when a is very close to b. No matter how close a is to b, sine a minus sine b is smaller than that difference. Okay, so that's the example given in the book. Okay, so we have some more applications. 5. Let us do example 5 from the book. So this is something that we are supposed to do in every section, so that if it shows up in the exam. Okay, so another problem. So example 5 says, suppose f of 0 is minus 3. So suppose we have a function f such that f of 0 is equal to minus 3. Okay. F prime x is less than or equal to 5. F prime x is less than or equal to 5. How large can f of t, f of 2 be? Okay, so you have, so these are things that generally you run into. You have partial information about a function. So f of t, can f of t be, for example, 25? Okay, so for example, can we have f of 2 equals 25? Okay, so this is the question. So what you have in mind is you start from f of 0. You start from 0. At 0 it is minus 3. Its derivative is always less than or equal to 3. So derivative tells us how fast this function is increasing. By the time when we come to 2, can it be larger than 25? Okay. So what we can do here is we can do this in two different ways. Either you draw a picture. Okay, so the largest slope at every point is 5. Okay, so the function which fits to these definitions and is increasing fastest is a straight line starting from 0, its slope 5, and you check where it goes. Okay, so this is one acceptable, respectable solution. But since this comes after mean value theorem, so we have to push in mean value theorem here. You will see that mean value theorem is doing something similar. Okay? In the first proof, you will show that this is the fastest function, and it goes and hits, I think the number is 7. Okay? In the second proof, you will say that it cannot be larger than 7. Then you have to construct this linear function to show that it actually hits 7. Okay, so let's see. We can use mean value theorem, since this is an example after mean value theorem. So f of x minus f of, or rather let's say f of 2 minus f of 0 over 2 minus 0. Okay, nobody writes 2 minus 0 in real life, but if you are writing this for yourself, you write these things so that later on, if you suspect that something is wrong, you go back and now you know why you wrote 2 here. Okay, so this is equal to f prime c for some c in 0, 2. Okay, so from here we have f of 2. Well, okay, let's put f prime c less than or equal to something. Okay, so here, so this is less than or equal to 5. Okay, so let's put in values now. F of 2 minus 3 over 2 is less than or equal to 5. Okay, so f of 2 is less than or equal to 10 minus 3 equals 7. Okay, so f of 2 cannot be larger than 7. But can it be 7? Okay, so we want to construct, in this case, we want to construct a function satisfying these conditions, and at x equals 2, it is really 7. If no such function exists, then this is an upper bound. So for example, we could also say that f of 2 cannot be larger than 70, which is correct, but it's not satisfactory, right? Because we didn't get enough information about the function. You can, if you know that f of 2 cannot be larger than 7, you cannot answer this question, okay? Because it may be yes or no. Okay, so can it be 7? So consider the simplest function with f of 0 equals minus 3 and f prime x equals 5. Okay, so I'm trying to give my function the largest slope, the largest speed of increase. Okay, so what is this function? F of x is equal to 5x. It passes 5x minus 2, right? Because at 0 I want this to be minus 3. Okay, minus 3. Okay, so you check that f of 0 is equal to minus 3, f prime x equals 5. Okay, so those two conditions are satisfied. Now check f of 2. So f of 2 is 10 minus 3 equals 7. Okay, so the maximum of this function is less than or equal to 7 at 2. Of all these functions, the maximum number that can be taken is bounded by 7, but 7 is actually taken. Okay, so now we totally know everything about such collection of functions, and we can answer this question. The answer is no. Okay, because here we know that it cannot be larger than 7, and we know the 7 is taken. Okay, so I think we can stop here. On Friday, we'll continue more of mean value theorem.